So in the previous lecture, we looked at the paramagnetism of isolated atoms. So that might be atoms in a gas, or it could be atoms in a solid that are just sufficiently far away that there are no interactions between the magnetic moments. So in this lecture, we're going to look at relaxing that approximation and see what happens. Okay. So experimentally, it was found that very many paramagnetic solids, rather than obeying the Curie relationship where chi is related to 1 over the temperature, they obey this modified Curie relation, which we call the Curie vice. So if I draw some axes, here we go. So if we plotted 1 over susceptibility versus the temperature, if I had a Curie paramagnet, I would expect something like this going through the origin. So this is our Curie behavior. And experimentally, instead, it was found that this happened for many solids, that we get the same temperature behavior above some critical temperature, which we call the Curie temperature. So this is Curie vice behavior. But as I approach that critical temperature from above, the susceptibility becomes very large. What does that mean? It means that if I take my material and I apply a small magnetic field to it, I get a very big magnetization. Okay. What happens when I go below theta? Okay, what happens at lower temperatures? Well, then we find that the material becomes magnetically ordered in some way. So, for example, that might well be it could become a ferromagnet, or the spins wanted to align with each other. Okay. Now, Pierre Weiss was one of the first people to try to explain this, and he was working in 1907, pre the days of quantum mechanics. So he had no real idea what it was that was causing neighboring spins to want to align, but he just made a supposition. He said, let's imagine there's a field, which we now call the Weiss field, that causes magnetic moments to want to align. Okay. Now, in solid-state physics, we've got a choice often. We can do a very detailed calculation where we think about the interaction between a magnetic moment and its first nearest neighbors, and the second nearest neighbors, and the third nearest neighbors, and take into account all possible combinations. That's always a very expensive and difficult calculation. What we often do is make a mean field approximation. So we assume that each magnetic moment experiences a kind of average field from all of the others. Okay, and so Weiss assumed that there was a field that was felt by a particular magnetic moment, a particular atom, that was proportional to the magnetization of the sample. Okay, so the more the sample is magnetized, the greater this additional field at the atom center. Okay, and so the constant of mu naught is just fundamental constant. So the constant, unknown constant here is gamma. So now let's try and see if we can use this idea, and will we end up with a relationship for the susceptibility that matches what we can measure in experiment. So we'll start by considering an atomic site. So at an atomic site, there's a local field which we'll just call B without any subscripts. Okay, so B will be equal to B naught, which is the external, so the applied field, plus BW, which is our Weiss field. And we have that the Weiss field is proportional to the magnetization of the sample. Now, if we think about the individual atom, we can look at that and we can assume that that behavior, that the susceptibility at that site follows Curie's law. Okay, so we can define a local susceptibility at the atom chi local, which will be the ratio of the magnetization to the field at that atom. Okay, and this would equal C over T, and that is Curie's law. Okay, but this is not the susceptibility that we would measure in experiments, because while I can measure M, the magnetization of the sample, okay, I can't measure B, because B is the magnetic field at a particular atom, and I've no way of measuring that. The susceptibility chi that we would measure that equation 2 is going to be the ratio of the magnetization to the applied field, B naught. Okay, so that's what we can measure. But what I would like to do now is relate Curie's law to this definition of the susceptibility. Okay, right. So I will begin by using equation 1. Okay, and that tells me that mu naught m over b, but hang on, b is b naught plus b vice, okay, equals c over t. Now expanding that up would give me mu naught mt is c b naught plus bw. But I know what bw is because I can just substitute it in from up here. Okay, so that would give me mu naught gamma m. Now let's pull all the m's onto the same side, and we would get mu naught m t minus c gamma and c, and that would be equal to c lots of b naught. Okay, and I'm nearly there now. So if I use equation 2, okay, we know that the susceptibility that we measure is equal to mu naught m over b0. But from the previous equation, I can see what b0 over m over b0 is. This will just be equal to c over t minus gamma c. And if you like, I can replace gamma c with another constant, so I'll replace it with theta. Okay, and from this, we've derived the Curie-Weiss behavior. Okay, so this says that we can account for this experimentally observed form of the susceptibility simply by assuming that there is some field within a material that wants to drive neighboring spins to align. And if that's the case, we will have a material that is paramagnetic, and as we cool it down, there'll be some sort of phase transition, and we will get an ordered magnetic state. So here we have that derivation written out now in neat. Okay, so to summarize, here we have the Curie-Weiss behavior, and theta we know as the Curie temperature. So what this means is that when we're below theta, the magnetic moments will naturally align, and what we have is a ferromagnet. When we go above theta, the material is paramagnetic, and its susceptibility follows this Curie-Weiss behavior here. Okay. I mean, this mirrors a bit about what we know, say, about iron magnets. So probably you know that the Curie temperature in iron is about 1000 Kelvin, actually about 1000 Celsius. Pretty high. If we have something that is a magnet, if we heat it up above its Curie temperature, now that's still well below the melting temperature of iron, it will stop being a magnet. It will become paramagnetic. Okay. If we then allow it to cool back down again, well, that's quite interesting. Um, what you would find is it would be a ferromagnet. It would be strongly attracted to a magnet, but itself wouldn't be a permanent magnet. The reason being is it will have formed magnetic domains and they will cancel out the magnetism of the sample. A bit more on that later, but we could, if we say applied a magnetic field to it that was strong enough for a long enough time, we could make it back into a permanent magnet. So Weiss proposed that the idea of a field that wants to cause magnetic moments to align. But he was working in 1907, and it wasn't possible at that time to the physics wasn't known. Okay, um, what people initially assumed was perhaps if we imagine two magnetic moments. Okay, now it's certainly the case that this first magnetic moment creates a magnetic field, and so there must be a magnetic field created by this magnetic moment at this second site, and that could well, it would either align or anti-align the magnetic moments. Okay, but when people at Weiss did the calculation, the energy of interaction is really, really tiny. So you would only get ordering through this direct interaction if you were less than, say, 1 Kelvin. Okay, at any higher temperatures, there's enough thermal energy that it would destroy any sort of ordering. So the idea that this is responsible for something like the ferromagnetism in iron, where the Curie temperature, the ferromagnetism persists into over above 1,000 Celsius, is nonsense. Okay, so that can't work. So it wasn't until the 1930s, when quantum mechanics was more developed, that there was an appreciation of what it is that drives certain materials to have magnetic ordering. And it's a purely quantum mechanical effect. It's known as the exchange field. And as such, to describe this properly, we should really be writing down quite a lot of equations and playing around with them, and that will allow us to look at the conditions for when materials are ferromagnetic and when they're not. It's a lot of math, and it's not really very illuminating. What I'm just going to do instead is give you a rough idea of where this exchange field is coming from. Okay. So the idea of exchange goes back to, if you remember your quantum mechanics notes, it goes back to the idea that electrons are fermions, and if you have a wave function describing a set of fermions, that wave function must be antisymmetric, so change sign, when we exchange two identical fermions, okay, when we exchange two electrons. The consequence of that exchange behavior is something like the Pauli exclusion principle, which says that two electrons can't have the same set of quantum numbers. Okay. So what does that mean in terms of trying to align spins? Well, let's imagine we've got two electrons, each on different atoms, corresponding to some in some sort of orbitals. There they are. Okay, and let's imagine that they overlap. So there's a region of space in which the electrons can occupy the same. Both electrons can be there. Okay. Well, we've got two arrangements of the spins. We could arrange the spins anti-parallel. Now, from the Pauli exclusion principle, that's interesting because they've got different spins. So already these two electrons have got two different quantum numbers. So there's no problem with these two electrons occupying the same region of space. Okay, they're never going to have the same quantum numbers. So anti-parallel spins, electrons, can get much closer to each other. That means, so these can be closer. And that means a large Coulomb repulsion. Okay, because obviously electrons are charged, the closer they are together, the greater the Coulomb repulsion. Okay, the other situation we could have is we could have the spins parallel to each other. Now they've got the same spin quantum number. So there's a exchange basically drives these electrons to be further apart from each other, to not occupy the same region of space. Okay, so they become further apart. And this means that they have a lower Coulomb energy. Okay, and it's a very subtle effect. We only need very little changes in the distribution of the atoms to give quite a big change in the Coulomb energy. Okay, so magnetism is quite as this ferromagnetic ordering is a very subtle phenomena. It just needs very small changes in energies to say why something is a ferromagnet and another material isn't. Okay, so just to summarize, what we're saying is the exchange field means that having two neighboring spins parallel to each other is a lower energy state than having them aligned anti-parallel. Now, there are various mechanisms, other mechanisms by which exchange can happen. Okay, it's very ubiquitous. It can take place in insulators, it can take place in metals, and in both, the mechanism of how it happens is a little bit different. But the good thing for us is that we can describe it by a very similar term. Okay, so irrespective of what's actually happening at the electronic level, we can write down an equation like this that describes an exchange energy. So here I've got the case whereby if my two spins are parallel to each other, and if J is positive, you can see that that's the low energy state. Okay, so if J is greater than 0, this will imply ferromagnetism. Okay, larger J exchange is, okay, that's related to the energy difference really between these two, between these sort of configurations. The greater the drive for the material to be ferromagnetic. Um, I'll just leave you with an observation. We'll come back to it in a couple of lectures' time, but there could be materials in which J was less than 0. And you might want to think about what would that mean in terms of, so this is the one where the spins want to align like this. This would be energetically favorable. So if J happened to be negative, what would that mean for the magnetic ordering of the material?